Well, thank you. I always love doing these presentations. I have done a few of them, and usually it's on a topic like birds was my latest one, flowers, berries, etc. And those are all fun topics. Tonight's topic is important, and I'm happy to be able to be here and speaking about it. My topic tonight is Alaska in transition, important events in the climate and weather of Alaska, and some of the ramifications of those changes in the weather patterns that we're seeing. So, do put your comments, questions in the comment boxes, and they'll be read aloud to me, and I will answer them as best as I can. So, information that I'm going to be sharing tonight is from different presentations that have been presented at the Alaska Forum on the Environment in 2019 and 2020. I've gone to a few actually before then, but I really started collecting information during those two sessions. Because there's a lot of information coming out. And a lot of information is actually coming out from IARC and ACCAP there, the International Arctic Research Center and the Alaska Center for Climate Assessment and Policy are doing a lot of research about what is happening with the weather in Alaska and what is happening because of the changes that we're seeing. So I went to their websites and got current information that included this last year as well. And the National Weather Service just put out information, kind of summarizing information from the last 30 years, which is really helpful. So I had actually seen some of these changes myself during my lifetime here, and those changes were built on changes that I heard old timers talking about when I was younger in this area, and over my life and then the stories, it's kind of a remarkable change that we're seeing. So what's going on here? There's been a number of notable events in the last few years. In Bering, we've had the 5 warmest summers, 5 warmest winters in the previous 5 years there. Warmest month statewide was July of 2019. We've had flooding, we've had wildfires, we've had coastal flooding. Earliest breakup of the Tanana River ever was in 2019. Record heat in Anchorage, 90 degrees Fahrenheit in 2019. Record heat around the whole state. This graphic actually is not showing up all that well. There's a blob in the marine heat wave. I'm going to talk about that a little bit more. Southeast Alaska, I'm going to talk about Alaska in general and then also about Southeast Alaska kind of in particular at the end since we're in Southeast down here. Last summer we had the wettest summer on record. Previous 2 summers were drought years and drier than usual. And the summer before that was a really super wet summer. So we've gone from extreme to the other extreme and then back again in just 4 years, which is pretty remarkable. Record low sea ice extent we keep breaking that record actually. I'm going to talk about that a little bit more. And then coastal flooding is continuing to happen. And part of that is because of the low sea ice extent. Part of it is because of the melting permafrost as well. So weather pattern changes. What are we actually seeing happening? Well, as you can see in this graph here, this is from ACCAP there, and you can see from 1900 up to 2020, that's a lot of decades of information. And you can see the green trend line here is that it is, over time, getting warmer on average. And the 10 coldest years are all previous to 1980. And the 10 warmest years, 9 of them are since 1980. So it's like 1980 is kind of I'm not quite sure why, but a little bit of a dividing line there. There was one warmer than normal year in the 1920s, late 1920s. But other than that, the other 9 warmest years on record, 9 of the other 10, are all after 1980. So Alaska as a whole, the average temperature has warmed up by a few degrees over the last few decades. It's not warmed up evenly, though. There are some places that have warmed up more than others. Here in Ketchikan, it warmed up by about 2.5 degrees Fahrenheit from 1970 to 2019. You can see that in the upper left-hand corner. The rest of the south central Alaska, about 3 to 4 degrees Fahrenheit. And then up on the north slope is the warmest. gain there was more than 6 degrees Fahrenheit since 1970, which is that's a lot. That's a big gain there. So that's a really remarkable change. And as it states, that this is statistically significant too. So that's remarkable. So in addition to the overall warming, there are fewer and fewer great cold snaps. It used to be colder in the wintertime periodically. So this is again from 1930 up to 2010. And prior to 1980, there were several years. You got down to, minus 48, minus 50, minus 54. Since 1980, there has not been a cold snap that was colder than minus 43, which is a pretty good difference in temperature there. So with the overall warming and then fewer really super cold snaps, that paints a pretty clear picture there. This is, of course, only in Fairbanks, but that's kind of right in the middle of Alaska there. And so if it's having fewer cold snaps, probably the rest of Alaska is as well. A good indicator place right there. Precipitation trends are also really changing. Overall, there's more rain, as you can see here. Plus 4% down here in southern Southeast Alaska, plus 10%, plus 14% up in the northern Southeast Alaska. Up on the North Slope, plus 12%. On the west coast and on the east, kind of by Canada, almost 20% increase in precipitation since 1970. And that is really huge. That's a big change. A lot more precipitation and warmer is a big difference. That kind of adds up to a difference in growing season as well. So up in Utqiagvik, formerly known as Barrow, the growing season has increased by plus 334%. And that's like 3 times as much growing season as there was before. And that's enough time for, that's a huge gain. That's unreal gain in the growing season. That's going to radically change the type of plants and how big different plants can get in that area. Further south, Kotzebue is plus 34%. Over Northway, plus 13%. Fairbanks area, plus 31%. Down around Ketchikan here, plus 4%. So not that much of a difference here. The further north you go, the bigger the difference is in the growing season. So we're not really seeing much of an effect on that right now. Could potentially in the future. And looking at the rest of Alaska and seeing how much of a change is happening there, it's reasonable to think that we might have a continued increase in our growing season, which may not be terrible, really, but it is a change, and it's going to change what can grow where. So that's something to keep in mind there. This is an interesting graphic. It shows the Alaska snow season length from 1997 to 2018. And it goes from 1997 at the top down to 2018 on the bottom. And then along the x-axis is the range from September 27th to June 10th. So basically, how long is the snow season? How long is winter? Basically, right? And it has become compressed. At the top there, you can see that the trend lines are wider, and that towards the bottom, the trend lines are narrower. So the snow season has been compressed from a longer snow season to a much shorter snow season. The trend line, and I can clearly remember when I was young here, a number of decades ago, the first snow almost always happened sometime in the last week of October, measurable amount, like an inch or so of snow. And now, and you can clearly see in this trend line, is that has been pushed a little bit further into like November kind of a time frame. Spring is also happening in general much earlier. So that kind of goes along with the growing season, increase in growing season, decrease in snow length. Okay. So a summary of all of that, the temperature has basically increased during all seasons across Alaska. Precipitation has increased, mostly happening in the fall and winter. Snowfall in general has decreased throughout the state except over 10,000 meters in elevation. Still quite a lot of snowfall there. Some of the changes are pretty big to the change in temperature and change in precipitation. In some areas it's smaller, but small changes can have a big effect. And then of course the bigger changes are going to have an even bigger effect. There are regional differences, kind of microclimates here and there. We know that even just looking at Ketchikan and one end of the road system versus town versus the other end of the road system can have variability in snowpack and et cetera. This is definitely like statewide big picture. There's some variation regionally, and they're studying that too to be able to figure out exactly kind of what's going on where, but localized details are handy for those of us living in different areas. But okay, so in Anchorage, this is some of the information that just came out of the National Weather Service and NOAA as a comparison of the 30-year climate normals. This is for Anchorage. And they've got these first columns a little bit interesting here, but anyway, max temperature and minimum temperature, mean temperature for 1980 to 2010, 1991 to 2020, and then the difference, how much of a change things have happened in maximum temperature, minimum temperature, mean temperature, precipitation, snowfall. And in Anchorage, there's been a little bit of warming, a little bit less precipitation, but more snowfall. And that's kind of interesting. So now going into like one of the topics, what's going on because of these changes in the temperature and precipitation. And one of the big ones that's having an enormous effect on Alaska as a whole is the melting sea ice in all of the oceans around Alaska, northern part of Alaska and the western part of Alaska. Normally have a lot of ice throughout the wintertime, but that's been changing and there's less ice for less duration is the main thing there, and that is really having a huge impact. So, since 2000, so that's not, since 2000, there has been a 25% decrease in the Arctic sea ice extent in September. So by September, it has melted back as far as it's going to before it starts refreezing and becoming, more ice throughout the winter, right? So it's been melting back further and further, a little bit of variability each year, but overall, there has been a 25% decrease in the amount of ice still left in this September when it has melted back as far as it's going to melt. So in the 40-year period since satellite measurements began, the annual minimum sea ice extent has decreased by 33%. It's a third less ice than it used to be when it has melted back as far as it's going to for the summer. The Arctic winter sea ice maximums were at record lows from 2015 to 2018. It's kind of come back a little bit since then, which is really good. Hope that it kind of has that trend continue. The melting pack ice then also affects the permafrost, which is also melting, because that cooling from the pack ice kind of helps keep the permafrost, especially along the edges of Alaska, from thawing. And so with less ice, more permafrost is thawing, which is kind of a side effect that's not so great. And then another part of that too, overall warming, is that Alaska has some of the fastest glacial melt rates on the planet. Our glaciers are melting. The pack ice is melting, the permafrost is melting, the glaciers are melting. So actually, basically, Alaska is melting right now. So this is a graphic showing the spring meltout date of the Bering sea ice extent. When does it really start melting out? Where does it go, The smooth line, the trend line there shows that it is happening earlier and earlier and earlier in the year. So this is from 1980 to 2020, and it has gone from just before June 21st on average, all the way down to a little bit before June. So it's about 3 weeks earlier than it used to be. And that's a huge change. This is a little bit confusing. All of the gray lines you can kind of see wiggling around are different years. The red line is the average or median from 1981 to 2010 of the Bering Sea daily ice extent. And then the blue line is the 2020-2021 winter, and then the green one is the 2019-2020 winter. And it's showing that our two most recent winters basically have less ice than the average has been for the number of years. So that's kind of also not great. Yeah. The sea ice extent is on the left-hand side there in square kilometers, so that just the area of ocean that is covered by ice. And you can see here that the red is the ice, and here's Alaska, anyway there, and the red comes down at least usually halfway down through the Bering Sea, sometimes a little bit further than that. So, yeah. So not only does the sea ice melt out a little bit sooner than it used to, it also forms later in the fall. So there is open water all the way around Alaska for a longer period of time each year. Melts out sooner in the spring, refreezes later in the fall. And its average in September, this is just a graphic that shows in 1988, September, the average was actually still fairly close to the northern part of Alaska. And in September of 2018, it was substantially further. And then something that's not mentioned here is that not only is the area of ocean that's covered by ice smaller, but the thickness of the ice is also reduced. So there's just a lot of less ice. There's less ice. This is the Chukchi Sea. So the Chukchi Sea is this is Alaska, right? Ketchikan's down here. Chukchi Sea is up here, above Alaska. And this is showing when the autumn ice over date, when it actually freezes over. And then again, like right after 1990, kind of 91 or so, the trend line all of a sudden takes an abrupt upward angling turn here, showing that instead of freezing over clear to the North Slope by, early mid-November, November 21st, it's now not freezing over until December 21st, so about a month later now, which is really huge, actually. The sea ice actually has a few different functions. One of the functions is to cool. I mean, it's a reservoir of coldness, basically, and keeps Alaska kind of cooled off, right? Once it has frozen and is land fast, it also protects the land from erosion, and it keeps the permafrost in that area more frozen as well. So having the ice over happen about a month later means that there's often open water during the first winter storms that come in, and then they can do a lot more damage through erosion, which is not good. Sea ice also affects the whole food chain, the food web. The underneath side of the ice actually grows algae because it just does. We're going to just leave it at that. It grows algae. And that algae feeds other things in the whole food. It's the bottom of the food chain. It's like the grass that we see around, feeds different things, right? It's the algae is the plants of the ocean, as far as primary productivity and driving the whole food web. So that algae that grows on the underneath side of the pack ice feeds the whole food chain, and with less pack ice, there's less algae production, which means that the food web is not being supported as well. So in the years when there was a lot less ice in the whole region, there were massive bird die-offs, and at first I thought, well, maybe PSP, kind of harmful algal bloom, something killing them, but there were no toxins in the body during those massive bird die-offs, and the birds just looked like they'd starved. And so that's pretty concrete evidence that not having the sea ice there with the algae production just really impacted the food web that much. One of the kind of interesting things that's kind of come out of this, these changes are happening quite quickly, and there's a few different organizations that are working on like tracking what's going on, but they can't do all of it. And so they have actually partnered with different communities, and there's a lot more like community science, citizen science kind of stuff that's happening now with different communities in like Western Alaska, Northern Alaska, because people have been living there for thousands of years, right? They have information already. They're helping collect more data and are actually helping track what's happening a lot more, which is pretty great, actually, having that community response and the community science going on. So these are just different pictures of birds that are, and I wanted to in particular point out the kind of bottom couple here, the unusual fishing conditions, the lack of algae in the back of the pack ice, bottom of the pack ice are also affecting fishing conditions. Also the change in temperature in the water column is changing the fishing conditions, and then the poor condition of the annual die-offs of seabirds is linked to that as well. So, and those things have been documented, first noticed and documented by people who lived in the area. So, yeah, that's, so sea surface temperature, along with the melting ice, goes, of course, along, the sea surface temperature is also increasing. This ended up being kind of blurry, but in general, the red has become much warmer than normal. In this October of 2018, it was much warmer than normal there. So I think it was, if I'm remembering correctly, it was like 2.5 or 3 degrees warmer than normal Celsius, which is a lot. That's a huge change. You can also kind of see part of the blob of warm water that's in the North Pacific over here too. I'm going to talk about that more in a minute. This is a picture that shows that in February, this was taken February 10th of 2019, and I listened to the person, she flew in from Nome to Anchorage to do a presentation about the different changes she was seeing in her area there regarding sea ice melting out sooner, and all the stuff I'm talking about right now, actually, she presented about. And as she was leaving Nome and flying over, she could see that there were these big leads of open water in February, and there should not have been any open water anywhere in February. That area there doesn't usually thaw until like May, so this was months earlier than normal, and she was completely blown away by this, and it was really powerful actually to sit there and listen to her be so immensely impressed by this huge change. And she'd been studying it and living in that area for a long time. So that year, actually, that Iditarod had to actually reroute to go around that area to get to Nome instead of crossing it as they normally do, because the ice was that gone, melted. So it, in the last couple of years, has frozen as normal. So this is not the new normal. It was an anomaly, but it might be pointing towards the new normal. That's the guess. So this is an important thing. The top picture there shows and what the bottom, not the surface temperature, but the bottom temperature is like normally in 2010. Mostly blue, pretty cold, right? Clear up to Nome. Really close in towards Nome, it's a little bit warmer, shallower water, that's understandable. But out in the Bering Sea, it's blue and cold, clear to the bottom. In 2019, and remember this is the same year that that ice melted off of that area much earlier than normal, the bottom temperature was much, much warmer. It was, 2 or 3 or 4 degrees warmer, 5 degrees, 6 degrees warmer than normal. Celsius, not Fahrenheit, but Celsius. That meant that with that cold water pulled way back further north, warm water had moved way up in there, clear to the bottom, warm water. That thermal barrier had been removed. And so that thermal barrier being gone meant that there could be massive shifts in the populations of fish. And so all of a sudden, people were noticing that there were pollock and Pacific cod that had moved up towards Nome. They had never been there before. They usually are kept down in the southern part of the Bering Sea, not up into the northern part of the Bering Sea. But they followed the warm water and food and moved north. And then the population increased of those two large predatory fish, the pollock and Pacific cod. Pollock population increased in the northern area by Nome by 5,421%. Pacific cod population increased by 1,153%. You're like, wow, okay, new fish, that's cool, right? We can eat these, they're edible, yeah. Small foraging fish that are normally found in the Nome, outside of Nome, northern Bering Sea area, of smelt and Arctic cod are really tasty, and the forage, those large predatory fish ate them. So the population of the small foraging fish, the smelts decreased by 70%, and the Arctic cod decreased by 100%. If you have a 100% decrease, that means they're gone. They couldn't find any. They were eaten. Arctic cod were eaten by the pollock and the Pacific cod. And that's really a huge change. That's massive change. Immediately, and people, the pollock and Pacific cod moved north following that warm water, and the non-trawl gear fishery also moved north to continue catching them even further north. And so they were catching them. That's part of why we have the information that we have. And nobody knew that was going to be happening. There was no regulation about whether they could fish in that area because they'd never been, physically never been able to. There was never an excuse to have any regulation. So they just followed them up there. And people who lived in Nome were like, why are there bright lights way out there in the middle of what? What is going on? That was one of the first things that helped them realize that this big shift in the fish had changed, was noticing that those big factory trawlers were out there fishing and catching them. Why are there those bright lights? Maybe we should go out there and figure that out. And so that's a humongous change. That's really only lasted not very long, actually. The following year, actually, that cold water barrier had been reestablished by quite a bit, and then this last winter even more so. So that was, again, an anomaly, but might be a harbinger of what might come, actually. So 2018 summary, Bering Strait region, unusually warm seawater was sustained for a long, months-long period of time. There was a massive seabird die-off due to starvation. The harmful algal bloom toxins were not the cause of that. There were several mass strandings of seals that occurred during the spring through the Bering Strait region. And those also had poor body condition, so they starved as well. Harmful algal bloom results were pending, but people that I was listening to present about it were saying that they didn't think that there was going to be any toxins in them. That it would be similar with the birds that they had just starved to death. There were multiple agencies and shipboard scientists that worked together, which was good. There's been a lot more information sharing instead of having different organizations kind of want to work alone and do their own thing. There's been a lot more information sharing. So a good thing is that in 2018 there were low levels of algal toxins throughout the Bering Strait region. Chukchi Sea, though, which is above Alaska, had high levels of algal toxins in the sediments, and bloom levels, which is like lots of them, right, offshore. So in some areas there are some pretty substantial algal blooms, depending on the year. So again, a summary of the Bering Sea ecosystem, what that means with the changing ice. So a loss of sea ice really equates to a transitioning of the marine ecosystem. That lack of a thermal barrier allows fish to move to places they've never been before. Less algae means less food for the rest of the food chain. Warmer sea surface temperatures don't hold as much oxygen, which is not really great either. There are cascading ecological effects. It's like a domino effect with one thing changing, then it's just like thing after thing after thing changes. For example, there are fish, bird, and wildlife shifts and movements, body condition of them are harmed, and then what would normally eat them is also affected and such. So industrial activities are responding, because if the fish are moving, then the industrial fishing is going to go with that. So current conditions at that time, this was in February of 2019, the severe cold had been reestablished in that area, but they weren't sure if it was going to be enough to actually really freeze the ice as thick as it really should be. And they were worried that it was going to be weak ice. And so ice did reestablish, but it hasn't got that ice that persists year after year after year after year has a different a composition, basic kind of texture, stability. New fresh ice doesn't last as long. So continuing on here, permafrost melting, like I was mentioning. With the pack ice melting, that affects how much cooling there is on the land as well. They kind of feed into each other, right? So permafrost is the soil saturated with water, frozen solid. And the further north you go, the more solid it is, the deeper it is. It's called continuous permafrost, because all of the land above, I don't know, what is that, the Brooks Range? Anyway, and the whole north slope is continuous permafrost. The top layer will melt a little bit in the summertime, maybe only 6 inches. It's not very deep, but just enough to be able to allow some things to grow. Supports a huge bird population, actually. A lot of the migratory birds that are going through here right now, or just getting done going through here, are actually headed up there, because all of that water doesn't go anywhere. It just hangs out there, breeds a lot of insects, and birds like to eat them. So they go up there and eat a lot of bugs, breed, and then head back south, okay? So that continuous permafrost is important for a variety of different reasons. The southern half of like the main part of Alaska there is called discontinuous. So there's patches of permafrost, areas of no permafrost, and then it's not as thick. It doesn't actually freeze as far down in the soil. And then the Aleutian chain, really southern, southeast Alaska, south central, and then southeast Alaska don't have any permafrost. That permafrost is melting, though. A lot of it is melting throughout Alaska, especially in coastal regions. So this is a graphic that shows the Seward Peninsula, Nome area, right? This is, of course, remember, this is the area where it's right adjacent to the Bering Sea, which is not always as frozen as it should be anymore, right? The current conditions show some permafrost is the blue, continuous permafrost, which is what really should have a lot of it there, is just the yellow, and then there are some areas of red that have no permafrost. Later this same century, the projected expectation of what the permafrost is going to be doing then is that I don't see really any yellow in that second picture there. A lot more red, which is no permafrost, and not as much blue, which is some permafrost. So that's a huge change, and that's going to be a problem. It's going to be a problem because all of that soil that is saturated with water and then frozen, the freezing of it holds all of the sediments together and prevents it from being eroded away very much. And so as it's thawing, and especially along the coast, the northern part of the coast and the western part of the coast, it's eroding away. It's melting, it's eroding away. Villages are having to move. It's really it's a problem. They've done measurements along the whole north coast of Alaska, the Beaufort Sea and the Chukchi Sea, and showing how much shoreline change, how much land they are losing each year in these different places. And that ranges, there's some places that are actually gaining. All of the blue shades are areas that are actually gaining a little bit. The dark blue is actually gaining about 15 to 36 feet a year. On the other hand, though, all of the yellow and orange and especially the red is losing. And the red dots, which there's quite a lot of, is losing losing 15 to 61 feet of shoreline a year. And if you keep doing that, 61 feet in a year is a lot of shoreline. And so that's a really substantial change. And that is a combined kind of factor with the sea ice not freezing solid to the land as soon. So like I was mentioning earlier, that extra month of time that doesn't have the ice protecting the land allows winter storms to really impact that. And then with the permafrost also melting and destabilizing all of the sediments, that's a real double whammy as far as the erosion is concerned. And you can lose a lot of territory pretty quickly if it's not frozen solid and there's a big storm that's able to wash it away. So that's kind of a problem. Luckily, Alaska's big. It's not just the coastline either. Some of the river banks are also really losing a lot each year. So coastal storm damage. Since 2000, we have spent about $200 million on disaster relief and storm damage. 16 state and federal disaster coastal storm events have occurred. Some communities on the coast have had to relocate. There are famous pictures of houses that were built, reasonable distance from the coast, that now the coast has been eroded away and they are, tipped off the edge in like half in the ocean now, which is pretty amazing. Average rates of erosion on Alaska's coasts are nearly 5 feet a year. Some areas are seeing erosion rates as high as 70 feet a year, and in some places even more. We could see, 70 feet a year. There has been an increase in general in harmful algal bloom events. Basically, that's because warmer waters stimulate algal growth. Algae need sunlight and warm temperatures, the same as plants do, to a certain point. So with warmer waters and sometimes more sunlight as well, that really stimulates algae to bloom. And some of the algae bloom, there's only a few that are toxic actually in this area. Most of them are beneficial and are the bottom of the food chain. But when you have one blooming that is one of the harmful ones, you can get a lot of toxicity pretty quickly at that point. The effect is to both wildlife and to humans as well. So something to be kind of keeping aware of. This is outbreaks by month, and this is in Alaska from 1993 to 2014. And you can see by far the two most dangerous months of the year to eat shellfish, which bioaccumulate the saxitoxins that cause PSP, is May and June. It's never safe. There are events every single month of the year throughout Alaska. But May and June, really don't go eating wild harvested shellfish. You should get them tested. This is a kind of it's a count, basically, a comparison of PSP cases in Alaska from 1973 to 2014. And the first graphic is from 73 to 92, and then from 93 to 2014. And it's kind of hard to tell, but when you really study it, you can see that for every month, there's been a slight increase from the first graph to the second graph of all months. And then for the main, August, June, July, August, what is this? April, May, June. For April, May, and June, or May, June, July, there's even more. There's a few more cases each year, statewide. So, this is in people. There have been events that have been linked to birds, or sometimes it's kind of a little bit confusing. Some of the bird die-offs are because of starvation, because of a lack of pack ice, keeping the ecosystem going. Some of them are because of PSP events. Same with the marine mammals. So this shows algal toxins detected in marine mammals or seabirds, kind of a really rough estimate, basically a graphic showing kind of a rough amount of each different species that has been affected by this throughout the state of Alaska. And basically what you can really see is that with seabirds, whales, dolphins, seal species, sea otters, sea lion, and walruses, all of our marine waters throughout the state at one point or another in some place has had those different species affected by PSP toxins. The effect of the changes are widespread. Berries have been affected throughout the state. There are changes to berries availability throughout the state. It's either earlier or later, depending on the year and the area. Sometimes more, sometimes fewer. It's difficult sometimes, depending on the year, for people and animals to get what they need. And so if it's a boom year, that's great. If it's a bust year, it's not so much great. Flooding has increased throughout the state. 13 state federal disaster flood events related to ice jam flooding and summer-autumn rainstorms have occurred since 2000. There's been a marine mammal decline. Stellar sea lions and sea otters, not so much in southeast Alaska, but further north, have really decreased. So in stellar sea lions, the population has decreased by about 80% since 1970s to the early 2000s. Some is rebounding, but not very many, actually. And this is not that does not include southeast. Our populations here are doing fine, but in south central and at the Aleutian chain. In sea otters, the Aleutian Island population has declined dramatically. Since 1980, there's been a decline of about 95%. There's a few different threats that include, that have affected both of those populations. But climate change is one of the effects. And of course, these effects kind of add together and really have more of an effect, right? But climate change is one of the things that has affected both populations. Melting glaciers. So the cumulative Alaska glacier ice lost in billions of tons from 2002 to 2017 is pretty significant. And that trend line is about as clear as you could possibly get. Our glaciers are melting. Average annual sea surface temperature between 1900 and 2020. Again, really warmed up. The 10 coldest, 9 of them are before 1920. The 10 warmest, I think 7 of the 10 warmest are since since 2000. So that's pretty remarkable too. Part of that is due to the blob. This is a graphic here that shows a huge, much warmer than normal blob of water that extended from the west coast of, like, I don't know, California kind of area, all the way up into south central Alaska. So much of the North Pacific, the eastern part of the North Pacific, right outside of southeast Alaska, was much warmer than normal. Starting in May of 2015, starting in 2013, extending to 2016, this was established and was there for a number of years. And it really dominated in the North Pacific. It's dissipated. It is then, last year was maybe coming back for a little bit, but that's kind of dissipated again. And it was deadly to salmon. It was deadly to birds. It was deadly to other species, and it was much warmer than normal. So our salmon stocks are still being affected by that happened. So that's starting to hit us where it hurts down here when the warmer than normal water is affecting our salmon populations. And then in the interior, main big fish streams in the interior had massive die-offs of thousands of salmon that died before they spawned in the summer of 2019. Same summer of 2020, not quite as bad, but same deal. And the reason why they died, they got into the streams really hot years, and the water reached or exceeded 70 degrees Fahrenheit, which is really, really, really warm. It can't hold enough oxygen. The colder water could hold more oxygen, so this warmer water didn't have enough oxygen in it. The warmer water also increased the metabolism of the salmon, making them need more oxygen during a time when there was less oxygen, and they just died. And that's a huge hit to the salmon populations up there. Something else that's happening is, as the state overall is warming, the tundra is greening up. The green areas are greener than normal. The brown areas are browner than normal. So the vegetation growth is already being affected by the changes in our weather patterns that we're seeing. What's this going to mean? Not quite sure yet, but it is changing. Beaver are expanding now. This is kind of truncated a chunk of the top of Alaska, right? The North Slope and then down to about Fairbanks area. And beaver have managed to kind of get around the end of the mountain range there and are expanding back up into the North Slope again. And they are masters at changing the hydrology and the water dynamics of an area. And so that's going to be a big change too with beaver moving up into that area. So changes in Southeast Alaska, kind of what's happening down here. Well, back to the 30-year climate normal comparison that the National Weather Service just put out in Yakutat. They've had a change in temperature, increased maximum temperature, increased minimum temperature, increased mean temperature a little bit, and a decrease in their precipitation by almost 15 inches a year. That's so lucky. Juneau, increase of their maximum temperature, decrease in their minimum temperature, so it's kind of spreading a little bit. Mean temperatures, no change. Precipitation, almost 5-inch gain in precipitation, and almost an inch gain in snowfall. So not a huge change. The precipitation's pretty substantial. Almost 5 inches more is quite a lot. Sitka, no change in the maximum temperature. Minimum temperature has warmed up a bit. Mean temperature's warmed up a bit. A little bit less, almost 3 inches less precipitation a year. Ketchikan, our maximum temperature's warmed up. I know you're shocked, right? Maximum temperature's warmed up a little bit. Minimum temperature's warmed up a little bit. Mean temperature's warmed up by almost a degree. And, oh, we are so shocked to know that we are getting about a little more than 8 inches of rain a year, more than we used to. So, yeah, that's even with the 2 drought years that happened. Just a couple summers ago, right? This is in Juneau, so kind of the closest information I could find, but this is days per year with a high temperature of 70 degrees or more, and since 1950 until 2020. And there are, over time, years when you have, 30 or plus days of 70 degrees or more. But since about 1990, 89, 90, there's been more of them, more frequently and more days. So in 2020, it was like 45 or something days with high temperature of 70 degrees or more, that's a big change. That's a big change. Heavy precipitation in Juneau, also increasing. Days per year with more than half an inch. I didn't know that half an inch of rain in a day was considered heavy, but okay. Anyway, Juneau is getting more of those days per year over time. Pretty clear trend line there. Sea surface temperature increase in Southeast Alaska is also increasing. That graphic didn't come out very well at all, did it? Sorry about that. But the trend in historic Southeast surface temperature has been increasing over time. The yellow cedar has been declining. This is something we've known about for decades. Took some figuring out why are this yellow cedar just dying off massively. And finally, people kind of figured out that the freeze-thaw cycles are killing them. In years past, decades past, when there was more snow, that snow would insulate the roots of the yellow cedars from the bitter cold snaps that would happen. And so, especially in the springtime, and so now with much less snow than we used to get, we still get those cold snaps periodically, and those can freeze down far enough to be damaging and killing the roots of the cedars, yellow cedars, and that kills them. There's a hypothesis people who are working on this are thinking that same quick freeze without a snowpack to be, or even any kind of protection for that, the similar winter conditions could be killing pink salmon eggs and juveniles in the gravel. That might be what's also killing those salmon. So, on the upside, as far as the yellow cedar decline, people are kind of studying and they're trying to figure out, and they think that there might be a compensation kind of going on for that. That the yellow cedar are maybe extending their range further north, because that's where it's hospitable for them now. And so we might be losing them in points further south, but we might be getting more in points further north, and so we might not lose them entirely. This is the historic range of yellow cedar, and the red, and in particular kind of in the northern Southeast Alaska, a lot of the yellow cedar have been killed off by the changing weather patterns. One of the things that's been happening in Alaska is, it's actually kind of one of the good sides of a lot of this. People are noticing, hey, wow, things are really changing, and this is all due to global climate change, which is due to CO2 being pumped into the environment by burning fossil fuels. And so with those changes being felt a lot in Alaska, more so than the rest of the United States, it's kind of got the attention of people and say, maybe we want to kind of do things that are not pumping massive amounts of CO2 into the environment, which is only going to make our problems worse. And so in 2010, the Alaska legislature enacted a non-binding goal for 50% of the state's electricity to be generated from renewable and alternate energy sources by 2025. And in 2019, only 9 years later, about 30% of Alaska's utility-scale electricity generation came from renewable sources. And those resources are predominantly hydropower, but also wind, biomass, wood being used for heat, solar energy. One of the things that was really jumped out at me when I was at the Alaska Forum on the Environment was listening to people talk about figuring out how to use solar panels throughout the state of Alaska for almost the whole year, even in the wintertime. Mounting them vertically so that snow wouldn't stick, and then being able to move them a little bit to track the sunlight, a little bit of sunlight there was. And through a lot of Alaska, people are using more and more are using solar energy for like home kind of level electric generation. And people are getting off of oil for their electricity generation and are moving to all these different ways, including solar in Alaska in the winter, and that's incredible. So we've been heading in this direction for quite a while. We're seeing the effects of having been headed in this direction for quite a while. But there's hope that, I mean, not just Alaska, but everywhere can be using more alternate energy and not be continuing to pump CO2 into the environment. So, Alaska is at the forefront of climate change, experiencing impacts faster than the rest of the United States. And that is something that is kind of interesting. We can see this happening much more quickly up here and gives us a little bit of an advantage, actually, sort of, in being able to react to it sooner. So, thank you. And does anybody have any questions for me?
I have a question about temperature change and its impact on migration of birds, because you talked about birds going up and snacking on permafrost insects, and mammals.
Things are migrating differently. Mammals, like the beaver I was talking about, that's moving further north. There are more rare birds, I think, that are, wow, what are we having? Why is this here? Different birds that are coming up. Ocean temperatures, when the years when the ocean temperature is warmer, we see more weird fish coming up here too, sunfish and whatnot. So it definitely affects birds and mammals and fish and such, the warming does. What's going where, so.